I am Pavlos Protopapas, and I will be your instructor for this class. I'm excited. I'm looking forward to the next 5 weeks with you. I want to start by setting the expectations and the goals here. Our responsibility is to give complete set of lectures, exercise, homeworks, and everything. That's our contract towards you. We're going to be answering your questions. We're going to be here to support you and guide you to the end. Now, your term, the contract we're going to make is that you're going to work through the program. We estimate how much effort you have for everything to be about 15 hours a week, okay? That's very hard to adjust because a lot of you come from different backgrounds. Looking at the survey, some of you have taken courses, some of you just start. That's okay. That's why we're here. We have a big team to support you all the way. You just have to put the effort though. Come to the lectures, make the exercises, come to the labs, do the homework. There's a unique opportunity in this course, in these courses in general, to have a very high ratio of teaching staff versus student. So take this opportunity, even though you may get busy, maybe it's a little bit overwhelming at the time. In most classes, you get either the asynchronous, so you don't get the support, or big classes. I just came from a class with 350 students. Well, of course, we have 65 TAs, that's Harvard. But in general, most people do not get the support you're gonna get through a class like that. I'm not saying Univ.AI is unique, but this is one of the great things to have this support. We have created a platform that it can work a little bit asynchronous, but that doesn't mean doesn't mean you should not come to the lectures. There's nothing more exciting than seeing a professor failing in front of you, okay? So, so come and enjoy the failures, because if it was all recorded, it would be all nicely polished. It's the same as going to the movies versus going to a theater. I find theater very exciting because there is the moment that you're afraid that the actor may fail. The same happening now. I'm about to fail and I don't know what I'm gonna say and I'm not finding my files. This happens, okay? So I think you should kind of promise us that you're gonna carry through. We're gonna be plugging into. If you fall behind, someone is gonna be bothering you, okay? There's a couple of things you're gonna see in this course. One of them is what I call ramping up. The beginning, for some of you, you may say, this is a joke. I know how to do this, okay? True, the beginning is gonna be easy. It's gonna get a little bit more complex as we go. And the homeworks in particular, they have very easy questions and they have the challenging questions. So if you find some of the exercise or the lectures a little bit too easy, promise you when you hit the homework will be much more challenging. Though, again, for expectations, it's introduction to machine learning and AI, right? We're not gonna be doing transformers. We're not gonna be doing inception networks here. Is introduction. So we're gonna stay true to the term introduction. Also, just to have expectations right, this is not introduction to programming. We expect you to know programming. If you don't, again, there's gonna be support for you to catch up, right? So we narrow down what we expect from the students, some programming experience, and maybe some ideas on machine learning. And that's our goal, right? We're ready. So let's start by showing you a little bit around. So this is how it's gonna look. Has anybody figured out what these symbols are here? The little emojis I put there, anybody knows what they are?
The eyes with the cross in them?
Well, there's many, there's eye, there's all these symbols.
Is a representation of planets?
Brilliant. It is the planets. And if you read my bio, I am actually an astronomer. So we're gonna start with, you started with the sun. So the first one is what? What's the first planet? Let's see.
Mercury.
That's a Mercury. Then we're gonna go to Venus, Earth, Mars, etc. Okay, so you're gonna learn the plans at least. And then when we go to the labs, you're gonna see we start with the motorcycle and we move to a rocket, okay? And then the homework's earth, water, earth, fire, air. Okay, air will be your project. Okay, so that's, you all know how to navigate this. I think we have session 0. So we have a chat room on the side. So I'm gonna ask you as a favor to use the chat room primarily for content and concepts. If you have any questions regarding logistics, we have the forum, please send it there, one of us will answer. Okay, are we ready to rock and roll? So we're here to learn how to do modeling. So the first thing, we're gonna define what modeling is. So what we're gonna make here, we're gonna assume that the response variable y relates to the predictor x. So the whole idea here is that we're gonna connect the input, which I call predictor, to the output, which I call response variable. So there's some relation between the input and the output. Now, if there was no relationship, we all go home and we stop doing this business, right? The whole point here is that there is some relationship and we're trying to find. Or even if there's no relation, we want to prove that there's no relationship, okay? So let's focus now on finding these relationships. And so we assume that the response variable relates to x. So I'm gonna assume there is some function, f of x, that takes me from the input to the output. Now, f is an unknown function, we don't know. This is the ground truth, expressing an underlying rule for relating x to y, okay? Now, on top of that, I'm adding a little thing called e, epsilon actually, which is a Greek letter epsilon, which it's a random amount of that you add on top of it, on top of fx, that makes the y to be different from f of x. Okay, so if you think about it, epsilon will be y minus f of x. So the difference between the y, what we measure, and the ground truth will be this epsilon. And for now, we say it's just a random amount. We'll be talking about that little epsilon as we go through this course, okay? So given input, we have some output, and there is a function, a ground truth that takes me from the input to the output. So a statistical model is any algorithm that estimates f, and we denote the estimate function as f hat. So the whole point is to put a hat on f, right? We're gonna spend 4 weeks together trying to put a hat on f. And you may think, why don't you put a hat on f and get over with? Well, f hat, it means estimate. That's what we're gonna be doing. We're gonna be estimating this relationship, right? So let's go to an example. So the motivation here is to predict the sales. Build a model to predict sales based on TV budget. So the response here will be y is the sales, right? And the predictor will be the TV budget. So notice I only consider for now one column, not all of them. Starting simple, getting that to work, and then we're gonna increase the number of predictors, okay? So let's think about a statistical model. So what we have an input x and y. So I'm taking my data. I only select 8 points. Why? Just to make it simple on the graph, easy on the eyes, right? So what we're trying to do is to find what is the y as some particular x. Okay. So what is the value of y, this x? That's a question we want to answer. Or another x, okay? So one simple way, so I'm gonna play with my PowerPoints and my PDF. So I'm gonna write this. So a simple way is to create a new model, which you're gonna say 1 over n, sum over yi, okay? So what, and then this I is equal to n, okay? So our first simple model does what? I am gonna take the average of all the Ys I have, all of my measurements, and I'm gonna call that my prediction for every X. So I'm taking all my points here, I take the average, and that's my first model. Kind of not the best model you've ever seen, but it is one model. It may be better than call a psychic network and ask for the answer, right? So we have one kind of a model. Of course, you all say, I can do better than that, right? Let's see if I can pick. I'm gonna do some cold calls sometimes, so you should get ready to answer. So Anirudh, Mr. Masur, that's easier for me to say. Do you think that model is good? Do you think you can do better?
I think that's good. But, can do better.
Yeah. Well, the idea now is we have some base model. We start with a very simple model we all understand, and our goal is to improve upon that, right? So let's improve. But before we try to find new models, let's identify the kind of models we want to do. So there's two types of models. One is called inference problems, and the other called prediction model problems. In the inference problems, we're trying to find the functional form of the f hat. In the prediction models, we don't care about the functional form. I don't care how the x is related to y. I don't looking for that function, the functional forms. I don't care to write the equation. The only thing I want to know is to give me the answer, right? So that's the two types. So let's do in a prediction model now, which is easier to do. I'm gonna do something and I'm gonna give you an answer back, right? So let's start with that. So the first thing I will do is the following. Let's assume I am a doctor, I have a sketch later, and I have a patient walking in. Actually, let's change the example. Yeah, let's keep to that. So I have a patient walking in, asking with some symptoms, right? This one way of doing it is I'm a doctor and I say, well, the last 5 years I've seen, I don't know, thousands of patients. This patient seems to be similar to other one I've seen yesterday. Maybe it's the same thing, right? So this idea of finding the nearest, most similar in my examples I have is what we're gonna be exploring now. So let's do that step by step. Let's say I'm trying to predict what is the value of y at some x. So I'm gonna first find the most similar one to that. And I'm gonna say my y is the same as the value of y of the most similar one. So the way to do that, first we have to find what is similar. And here we're gonna call similar the distance. So I'm gonna calculate the distance of x to all other x's. So that's gonna be my distance. And I denote that with the straight lines here. And then I'm gonna find the x, the example I have that is the most similar in the input, right? So I find this point here. If I'm trying to predict here, this point here is the most near, is the nearest to it, is the most similar in our definition of similar. So once I have that, what I'm gonna do, I'm gonna predict the y to be exactly the same as the value of the nearest neighbor, okay? Easy peasy? Give me some thumbs up. Not Harkun, the students. Okay. Now I can do it for every x, right? For every x, I'm gonna go, every x here, let's say, I'm gonna find my nearest neighbor. So if I'm here, I'm gonna look for all the most similar one, which is gonna happen to be this one. So I'm gonna predict the same. So if I move here, is again, the nearest neighbor is this. So I'm gonna move there. So I can do it for all x's now. And this is my model, okay? So I have a full model that predicts y for all the x's, okay? Now, this is kind of, I'm sure some of you say, why one? Why don't you do two? Why don't you do three, right? All right, let's do 2 or 3, since you asked for it. So I can do the same. Instead of find the nearest neighbor, I can find 2 nearest neighbors, 3 nearest neighbors, or whatever, k nearest neighbors, right? So if I do two nearest neighbors, for example. Again, I'm going to start with an X. I'm going to find the two most similar examples I have in my training set, which is going to be this one and this one. Now I have some Y values for them, the truth one. And then I'm going to take the average of the two, right? So I have this one and this one. So I'm taking the average, which is going to be that. Okay. All right. So I can do that for any nearest neighbor. So here I show you from my simple example for k is equal to 1, which is the blue line we saw before, right? This one, right? Then I can change to k is equal to 3, the 3 nearest neighbor, the 3 and most likely, which is going to be the dotted line here, and k is equal to 2 is going to be that. Okay. So let's go back to put a little more data to see the overall pattern, and you're going to do this in a second. So what do we have? We have, I did it for k is equal to 1, k is equal to 10, and k is equal to 70, and I plot my prediction. So you can see for as I increase the case, there is a pattern appearing, right? Good. So this is the diagram I was telling you before. What is k nearest neighbor? Let's sum it up. So it's the doctor here, nice cute drawing here. So the doctor sees a patient and he goes and sees the other patients he's found and find the similar patterns from the training. And then he makes diagnose by taking the average of this, of my nearest, the most similar patients the doctor have seen, okay? So k nearest neighbor, or KNN, is a very human way of decision making by looking at similar examples. KNN is non-parametric learning algorithm. It means no parametric, making no assumption of the underlying distributions here, which is plain straightforward. The algorithm, I wrote it down. I think you understand the intuition. I just have to always give you the mathematical background. So that gives me an opportunity to tell you how this course is going to go. It's going to have 4 pillars. One pillar is intuition. I think what you've seen now, I've done the intuition. The second pillar is going to be the mathematical background. We're not going to do typical math here, but we're going to not shy away from the mathematical rigor. And the third one, which is important, is the implementation. We're going to try things out. And the fourth one is that we care, that we really care about you and we want you to do well, okay? So given that, let me explain why I'm showing this. Is kind of the algorithmic, rigorous way of seeing it. So given a data set, we have x1, y1, and xn, yn. For every new x, find the k number of observations indeed most similar to x here. So I'm finding xn1, yn1, and xnk and ynk are the k nearest neighbors, and then I average them down here, okay? So that's kind of the algorithm, but I think the intuition you all got. I find the similar ones, average them, and that's my prediction, right? So you're gonna now see this A1 to exercise A1 and exercise A2 is on your at forum. We're gonna put you in the breakout rooms. And then the question is what to do when you're in the breakout room. I think you've done that yesterday in the session, but let's repeat. One of you will share. Today, the lucky student, they will be the student with alphabetically with the first name. So I see, oh my God, Amond, you're the lucky one. You have 2 A's at the beginning of your name. So you always been picked in everything first, right? Correct, Amon? How do you say Amon? Or your audio doesn't work. All right, but you hear us, right? Just give me thumbs up. Yeah. All right, so once you're there, make sure to read the instructions and the hints. Don't rush to finish the exercise. This is not a rush, not a race. The point is to learn. Don't rush to get everything working and click the mark. I want you to think about, talk to each other. It's an opportunity to get to know each other in the breakout rooms. And the best way to learn out the breakout room is to actively participate. All right, so let's go into breakout rooms. We'll be going around. By the way, just to be clear, it's okay to share code. It's okay to ask the TA to debug your code. Okay.
The TAs will make rounds through the breakout rooms, and all of y'all may have now a message to join your breakout.
Welcome back to part B. Did you enjoy your exercises? Did you feel the muscle pains already? All right. So I visited about 10 rooms, but I see everybody was moving along. Nobody was really stuck, but everybody was kind of slowly moving along, which is exactly what we want. So that means it's the right weight for you. So we're gonna move now to the second part. There's a couple of questions, I'll address them at the end, don't worry. Part B. Okay. Two more questions.
Yeah, so my question is with respect to minimizing the loss function. So for example, so the function that you just gave, so the loss decreases as you increase the value of x infinitely. So in that case, how would we, so ideally x has to tend to infinity for us to minimize the loss. But so then do we impose real world constraints like say budget constraints and then choose?
That's a very good observation. This particular loss function I gave you that is unbounded, you said, right? Because as s increases, x increases, this is gonna decrease. So this is gonna increase. And so yes, this one may be unbounded. Nevertheless, that was just an example, right? Is that what you're trying to say? You're not minimized with respect to x, you minimize with respect to beta, by the way.
So like in reality,
yeah, let me be precise so you don't, so this is gonna be sum over all the data yi log of 1 plus e minus beta x, right? So you said, now if you sum over all the data, this doesn't have to be necessarily bounded because there's another term here, which is, since you ask, it's gonna be log of 1 minus e, oh, sorry, 1 plus e to the minus beta xi. Okay, this is not bounded, so now I give you harder problems. So okay, go on. Sorry.
Yeah. So what do we do in case of unbounded loss functions?
Well, if it's unbounded and it goes to infinity, is obviously another good loss function. It means there is infinite minus infinity loss.
But I mean,
so
it's kind of practical, right? So for example, so if you imagine the budget versus sales example,
yeah,
it does make sense to say that if the budget is infinity, you would get the maximum amount of sales.
well, it's gonna converge at one point, you mean, right? That's not okay, so let's speak precise in the language. There is this problem, right? That it goes down, right? And then there is this problem that is like converges, right? So one is unbounded, but not converging, right, and the other is unbounded converging. This we can do, right? This I don't know what to do.
Okay. Yeah. So I was about the convergent ones.
So say again.
So about the if the because the loss function is when the loss function is convergent, and then we
this
have
one.
to minimize loss.
What do you do about that? Yes, if you're asking about that, what do? We need to put another constraint, which means that if I come to the point that the change between 2 points is less than something, I have to stop.
Okay.
Yep.
Thank you.
One final question. Your audio is very bad. It doesn't work. Too much noise. Sorry. Let's go to another student. Yeah, as I provide, your audio is just noise, sorry. You can type it or put it on the head. Someone else before I say bye-bye?
Uh, Professor, I have just one question from the beginning of the class, wherein we had shown us the linear regression line that, and epsilon would be equal to y minus fx. It's just a very random question where I was trying to think that, is it ever true in reality that epsilon would ever be 0? Because when I was reading the text in ISL, I read that epsilon is called catch-all, which means that if the relationship is not linear, if it is some other kind of relationship and we are trying to represent it as linear, then this epsilon would, it would contain whatever the relationship we've not been, or whatever extra information we've not been able to assess. So I just wanted to know if in reality is epsilon ever going to be 0?
Okay, so there's two things in the catch-all. One is the misspecification error, epistemic error, which means our model is not capturing the ground truth, right?
Right.
The other one is errors that they result from measurements and other reasons, right? Which is called irreducible error, okay? So the question, can epsilon be absolutely 0? Well, even if we come with the best model that fully captures the ground truth, they still have the irreducible errors due to measurements. Now, is it possible to have irreducible error 0? Means you have an instrument or some kind of measurement has no error at all? Well, no. I mean, the universe is full of errors. However, sometimes if you are not dealing with data, but simulations, then you may have a training set that has no error. So that in that scenario, your irreducible error does not exist, right? But it's very rare that you're gonna ever deal with that. So usually when we're dealing with data that are collected by instruments or by asking humans, will have errors, right?
Thank you.
So that little category of dealing with data, they are synthetic, so you don't have measurement error. That's very rare. It's part of my research, by the way. But yeah, in general, for the problems we're going to be doing, there is some stochasticity due to measurement, due to the way you collect data, etc. All right. One more and we go. I'm getting tired. All right, so this has been wonderful. Your questions are really, really good. It seems that you're having good questions, you follow. Please, let's connect the third pillar, fourth pillar, whatever the implementation. More comfortable you become with that, there's gonna be a couple of advantages. One is, more you know how to do this, more marketable you are, because that's how the real world works with real data. But also there's another advantage when you become very comfortable with programming. Some of your questions that you ask, you could ask actually experiment. You can actually do the experiments yourself. Oh, what if I add an extra term here? What if I simulate data with no error? Will it affect my results, right? So once you become good at writing code, you can even answer questions yourself. And the cycle will become shorter and shorter in the sense that I have an idea, let me try it. I write the code and I test it, right? Right now, I don't know your level, all of you, but some of you, I assume it's gonna take a little bit of time to put it together, right? But as you get better and better in that, will give you this opportunity to be able to experiment. So two things can happen. Either you become good or you become old and you have graduate students to do that. You choose what's the path you want to take, right? I've done both. I became good and I'm still able to run my own code, but also have graduate students like the TAs, some of your TAs here, that when I need someone to test something, I tell them to do it for me. So one of the two will happen. All right. So this has been wonderful. I really enjoy it. I really like your questions. Please fill up the quiz. Harkun, is the quiz available?
The quiz, yeah.
Yes, it is.
The post quiz. And then in the post quiz, there's a question, general, please fill it. It's about, I want to see you to write down what you think you learned. It gives me a good feedback to understand what I didn't explain well, what needs to be explained again, and an opportunity to ask some questions. I want the questions to be concise because we're going to try to answer them. Just few sentences with a question so we can really nail it down. Okay. All right. Thank you very much, and see you on Saturday.